Welcome to MathSoup videos. Today we are going to look at a problem called Collatz Conjecture, which remains as an unsolved problem in mathematics. This problem is fascinating because this problem is very easy to understand and to be worked out, yet it remains as an unsolved problem in mathematics. So the Collatz Conjecture goes like this. Consider a positive integer n. So n has to be a positive integer. And you perform the following operation on n. If n is even, then you divide n by 2. But if n is odd, then you multiply n by 3 and add 1 to it. So I'll repeat the procedure. Take any positive integer n. If that is even, then you divide it by 2. Or if n is odd, then you multiply it with 3 and add 1 to it. Upon repeating this procedure multiple times on any positive integer, eventually it will get reduced to 1. This is what Collatz conjecture claims. So the challenge is to find a positive integer which will not reduce to 1 when you repeatedly do this process. So let's take a few examples and work it out. So let's first consider some simple examples. Let's consider, say, start with n equal to 6. Now since 6 is an even number, I'll divide it by 2 to obtain 3. Now you'll repeat the same procedure on this new number 3. So 3, since it is an odd number, we'll multiply it with 3 and add 1 to it. So 3 multiplied by 3 is 9, and when you add 1 to it, you get 10. Now since 10 is an even number, again we'll divide it by 2 to obtain 5. And since 5 is an odd number, you multiply it with 3 and add 1 to it to obtain 16. Now since 16 is an even number, you divide it by 2 to obtain 8. And since 8 is again an even number, you will divide it by 2 to obtain 4. Now 4 is again an even number, so you divide it by 2 to obtain 2. And since 2 is an even number, you again divide it by 2 to obtain 1. So here we can see that in 1, 2, 3, 4, 5, 6, 7, 8 steps, the number 6 reduced to 1 by applying this procedure. Now, why did I stop at 1? So what happens if we continue doing this after 1? So that's again interesting to see, because if you continue the procedure after obtaining 1, then it will fall into an infinite loop. So since 1 is an odd number, we'll have to multiply 1 with 3 and add 1 to it to obtain 4. So when you continue after 1, you will again obtain 4, and since 4 is an even number, you will again obtain 2, which is again even number, so you'll obtain 1, and then when you repeat the process, it will form a cycle. So after 1, it will become 4, 2, 1, again 4, 2, 1, so on and so forth. So it just forms a cycle and then will repeat itself. So now the challenge is to find a number which will not end in 1 when you repeat this procedure over and over again. So let's try with another small numbers, because we are working this out without the use of a software for now. Let's take another small number and see whether we are able to arrive at 1. So let's consider, say, n equal to 8, or 8 is rather very direct. Let's take another number, say 9. So if you take n equal to 9, since 9 is an odd number, let's repeat the procedure. So since 9 is an odd number, 3 times 9 is 27, 27 plus 1 is 28. Now since 28 is an even number, I'll divide it by 2 to obtain 14. And 14 is again an even number, so I'll divide it by 2 to obtain 7. And since 7 is an odd number, I'll have to multiply it by 3 and add 1 to obtain 22. and since 22 is an even number, I'll divide it by 2 to obtain 11. 11 is odd, so 33 plus 1 will give me 34. 34 is even, so by 2 will give me 17. 17 is odd, so 3 times 17 is 51 plus 1 is 52. 52 is even, so divided by 2 is 26, which is again even, so divided by 2 is 13. 13 is odd, so 3 times 13 is 39 plus 1 is 40. 40 is again even, so 40 by 2 is 20. 20 by 2 is 10. 10 by 2 is 5. And since 5 is odd, 3 times 5 plus 1 is 16. And then you can now assume what is going to happen after 16. It will just be this cycle again, which we saw before, right? 16 is even, so it becomes 8, and then 4, and then 2, and then 1. And we can stop at 1 because after 1 it's going to be just 4 to 1, 4 to 1, which is going to get repeated. So when we started with 9, it took a bit longer to arrive at 1, but nevertheless we arrived at 1. So this is actually manageable for small numbers by hand, but if you want to try this out for larger numbers, we'll have to rely on some kind of a software to do the calculation for us. So as you can see, I am working this out in Mathematica platform. So let's just write a simple one-line code with which we will be able to check this out for larger numbers. So I'm going to write a simple while loop in Mathematica. So let's just write while. So the condition that I have is as long as n is greater than 1, I'll put an if statement. If the remainder of n by 2 is equal to 0, that means I'm checking whether the number is even. If it is even, then I want the number to be divided by 2, and otherwise if it is odd, then I want the number to be multiplied by 3 and add 1 to it. So once I do that, I just ask Mathematica to print the number n, and while loop will ensure that for any particular n, we can just continue this as long as n is greater than 1. Alright, so we can just define a value of n here. So let's first say n is equal to, we can just check whether what we have worked out by hand is true by running this code. So I have defined n to be 6, and then let's just run this one line code to check whether we are getting the same sequence. Here we go. So 6, 3, 10, 5, 16, 8, 4, 2, 1. 6, 3, 10, 5, 16, 8, 4, 2, 1. So we are getting the same sequence, which means we have not made any error while working this out. Right? So now I can just keep changing this n to see whether we are getting the same answer, right? So whether it will converge to 1. So if we start with n equal to 9, then you can see the same sequence here, right? 9, 28, 14, 7, 22, 11, 34, 17, 52, and ultimately it reduces to 1. So now is the fun part. So now since we have coded this, we can actually do it for much larger numbers. So let's consider a big number, like say a 2-digit number to start with. Let's take n equal to 60. Yeah, so it instantly worked it out. So when you start with 60, this is how 60 is going to reduce to 1 using the Collatz conjecture. So instead of 60, let's take say 99. It takes slightly longer than 60, and then you can again see that it is going to reduce to 1. So now let's just try this out for even bigger numbers, like a random number, like say 8, 7, 3, 4, 5, 6, 2, 3. So it's a big number. Let's see whether my machine can handle this calculation. So I'm just running this. Yeah, it took a bit of time, but then ultimately you can see that it started with this number 87345623, and then after so much of iterations we can see that it is again coming back to 1, right? So if I can just, you can have fun with this by increasing the size of the number and checking whether I'm just randomly typing. Okay, so it's like a huge number. Let's see, let's count how many digits are there. 1 2 3 6 9 12 15 18 21 25 26. So there are 26 digits. So let's see how long does it take. So it's still running. Oh my god, okay, it has finished. So it's a huge number, a random huge number with 21 digits that I have keyed in, and then we are performing this operation over and over again, and then we can see that it is reducing in size and eventually coming to 1. So I hope you enjoyed this video. I will encourage you, if you like the video, try working this out at home and use your own way to code it out and play around with these numbers. Thank you.